Find the equivalent capacitance of two capacitors in parallel, where one capacitor has a capacitance of 3 microfarads, and the other capacitor has a capacitance of 6 microfarads. If one of the two capacitors has a potential difference equal to 9 volts, determine the amount of charge on each capacitor and the charge of the equivalent capacitor. Let's begin with a sketch. We have two capacitors connected in parallel with each other. The first capacitor has a capacitance equal to 3 microfarads, while the second capacitor has a capacitance equal to 6 microfarads, which is double the capacitance of the first capacitor. We know that one of the two capacitors has a potential difference equal to 9 volts. Well, since these capacitors are in parallel, that means that they each have the same potential difference. And the potential difference across each capacitor is equal to 9 volts. We could use this information to find the equivalent capacitor of the two capacitors in parallel. Now we know that these two capacitors in parallel can be replaced by a single capacitor that we will call the equivalent capacitor. We know that the equivalent capacitor has the same potential difference as the other two capacitors, and that potential difference is 9 volts. We also know that the charge on the equivalent capacitor is equal to the sum of the charges of the individual capacitors. We also know that the equivalent capacitance is equal to the sum of the individual capacitances of our capacitors. So in this problem, the equivalent capacitance then is equal to the sum of the 3 microfarad capacitor C1 and C2, the 9 microfarad capacitor. So that means that our equivalent capacitance is equal to C1 plus 2C1, or 3 times the original capacitance, or 3 times the capacitance of capacitor C1, which means the equivalent capacitance is 3 times 3 microfarads, or for a value of 9 microfarads for the equivalent capacitance. Well, the problem says if one of the two capacitors has a potential difference equal to 9 volts, determine the amount of charge on each capacitor. Well, we could use the relationship that Valley College is quaint. This will give us the charge on the first capacitor. We know that the charge on this first capacitor then is equal to the product of its potential difference, and the potential difference is 9 volts, and its capacitance. The capacitance of the first capacitor is 3 microfarads. So to one significant figure, the charge on the first capacitor is 30 microvoltfarads, which ends up being equal to 30 microcoulombs. We could do the same work to find the charge on capacitor 2, which is equal to the potential difference across capacitor 2 times capacitor 2's capacitance. So the potential difference across capacitor 2 is 9 volts. The capacitance of capacitor 2 is 6 microfarads. This ends up giving us a charge on capacitor 2 being equal to 54 microcoulombs, well, to 1 sig fig, that is equal to 60 microcoulombs. So now that we've found the charge on both capacitors, let's find the charge of the equivalent capacitor. The charge on the equivalent capacitor is equal to the sum of the charges of the two individual capacitors in parallel. So this is equal to the sum of the product of the potential difference across capacitor 1 and its capacitance, plus the potential difference across capacitor 2 and its capacitance. Well, we know the potential difference across capacitor 1 and across capacitor 2 is the same because they're in parallel. So this means that the equivalent charge is equal to the product of the potential difference times the equivalent capacitance, which we already knew that because we know that Valley College is quaint. So that product of the voltage across the equivalent capacitor times the equivalent capacitance gives us the charge of the equivalent capacitor. So this means that we have the 9 volts for the voltage across the equivalent capacitor times 9 microfarads for the for the capacitance of the equivalent capacitor. And this is equal to 81 microvolt farads, which happens to be equal to 81 microcoulombs.